Earlier, we saw how oil can be reconditioned by filtering it. Now let's turn our attention to another method commonly used to recondition oil: vacuum dehydration. In this segment, we'll take a look at the basic principle underlying this method. In the next segment, we'll examine a vacuum dehydrator unit that is used to recondition oil. Vacuum dehydration is a process in which water is removed from oil by subjecting the oil to heat and a vacuum. Water can exist in oil in 3 states. These states are free water, suspended water, and dissolved water. Free water is water that has settled out of oil to the bottom of the equipment or container that the oil is in. Suspended water is water that is mixed with oil. It is attracted to solids such as cellulose paper insulation that are in contact with the oil in electrical equipment. Dissolved water is water that is essentially a part of the oil itself. Dissolved water lowers the dielectric strength of oil, which means that its insulating capabilities are diminished. Free water and suspended water can be easily removed from oil. Several different techniques can be used. Dissolved water is more difficult to remove. One way to remove dissolved water from oil is by vacuum dehydration. Vacuum dehydration is also efficient at removing some volatile acids and some gases from insulating oil. In fact, this method is sometimes referred to as degasification. The removal of gases is a side effect that occurs simultaneously with vacuum dehydration, whether it is needed or not. Degasification does not occur with other methods of water removal. A good way to explain the principle underlying the vacuum dehydration method is with a demonstration. For this demonstration, we'll use a vacuum flask that contains some insulating oil, a vacuum gauge, and a vacuum pump. The flask is made of clear glass, so we can see through it. Since it is only partially full of oil, there is a space for the vacuum to exist. Right now, the area above the oil contains atmospheric air. The vacuum gauge is used to measure the vacuum in the system. It consists of a tube and an indicator. Any pressure less than atmospheric pressure is considered to be a vacuum. On this gauge, pressure is measured in torr. Using this unit of measure, atmospheric pressure is 760 torr. The vacuum pump is used to create a vacuum in the system. After the vacuum pump is turned on, a vacuum is created as the pressure inside the flask drops. When the level of vacuum is around 5 torr, the oil will bubble or froth. The bubbles are composed of dissolved water and dissolved gases that were in the oil. As the pressure decreases, the molecules that make up the dissolved water and dissolved gases break free of the oil and form bubbles. These bubbles rise to the surface of the oil and burst. When the bubbles burst, the molecules go into the space above the oil, and the vacuum system removes them from the flask. By the time the vacuum level inside the flask reaches about 1 torr, most of the water and gases have been removed from the oil. Now, the demonstration we just watched showed the basic principle of vacuum dehydration. However, actual equipment contains components that make vacuum dehydration more efficient. For example, this is a vacuum chamber in a typical vacuum dehydrator unit. Inside the chamber, oil is pumped through this line to an area behind these fiberglass cartridge elements. The oil passes through the cartridges and fills the vacuum chamber. As oil passes through each cartridge, it saturates the fiberglass that makes up the cartridge. This cutaway of a fiberglass filter cartridge shows that a cartridge is constructed so that the oil passes over millions of fiberglass strands that have sharp ends. Having the oil pass over these sharp ends will make it easier for dissolved substances in the oil to form bubbles. The bubbles will rise to the surface of the oil and burst. Then the molecules that made up the bubbles will get sucked out of the vacuum chamber by the vacuum. We can get a better idea of what happens by looking at an ordinary glass of soda. The surface of this glass seems smooth, but it actually has many microscopic scratches and surface irregularities. The dissolved carbon dioxide in the soda forms bubbles at those parts of the glass surface. The bubbles expand, rise to the top of the soda, and then burst. Notice that the bubbles form only on the sides and the bottom of the glass, not in the middle of the soda. Now, a sharp point at the end of a strand of fiberglass has the same effect on dissolved water or dissolved gas in oil that a scratch on the glass had on dissolved carbon dioxide in the soda. Both serve as points for the formation of bubbles in a liquid. We can use this piece of fiberglass material from a filter cartridge element to illustrate this point in the context of vacuum dehydrating insulating oil. Now, the bubbles that we'll see do not come from air trapped in the fiberglass. There is no trapped air in the fiberglass. When the fiberglass is immersed in the oil, no air bubbles are released. We'll use the same oil we used in our earlier demonstration. Most of the dissolved water and dissolved gases have already been removed. When the vacuum pump is turned on, the level of vacuum eventually reaches 1 torr, the same level as before. Bubbles form around the fiberglass, but not in the rest of the oil. The sharp points on the fiberglass provide for further dehydration and degasification of the oil. So far, we've talked about the basic principle of vacuum dehydration. And we saw a couple of demonstrations of how water can be removed from oil by subjecting the oil to a vacuum and by using a fiberglass filter cartridge element. Read the material in your text that covers what you've seen here to be sure you have a good understanding of how vacuum dehydration works. When we come back, we'll wrap things up by seeing how oil can be reconditioned using a vacuum dehydrator.